This computer. Okay. Yes, I'm terribly bad at starting the recording at an appropriate time. So, okay, Julian, if you'd like to kick off, then take it away.
Okay, hoping you can see that. So very good. So hello, glad to be back, and thank you all for turning up. Perhaps it's all the rain that's made you come, probably not me. But anyway, I'm here to talk to you about galaxies, and 1 gigayear at a time is the title. So galaxies is something that we study at Nottingham. In fact, all the astronomy departments study galaxies. We are kind of a one discipline department. We only look at galaxies in the astronomy department. Other universities have quite a spread of interests, but everybody at Nottingham does galaxies. So I thought I'd better write something about galaxies as a talk. And you can actually see galaxies spelt out in Galaxies, and Julian Onions also spelt out in Galaxies. And there's a web link at the bottom there if you want to spell out anything of your own in Galaxies, because they come in all shapes and sizes. But anyway, just to be sure everybody's on the same page, I thought I'd better say there's not going to be much about chocolate in this. In fact, nothing at all about chocolate. So if you're all here hoping for something about that. Equally, the latest in mobile phones, it also won't be covering. We will be looking at things that happened a long time ago in galaxies far, far away, but not actually this film. So that's perhaps another disappointment, but maybe not. We'll see. But what I am going to talk about is galaxies, which are these sorts of things. You can perhaps see appearing on the screen. And this is all we study at Nottingham, but we don't really study many of these that you can see here because they're all a bit too close, and the science has kind of been done on those. So that's, you know, we look at much more distant and much less beautiful things, really. But just to sort of put it in context, this is a picture of the night sky taken by the Hubble Space Telescope quite a few years back now, called the Hubble Ultra Deep Field, and they stared at this tiny bit of sky, especially picked out because there was nothing very interesting in it. And after 11 days of exposure, it got this picture, which pretty much everything in there is a galaxy. And most of these are way, way out, right to the very edge of the visible universe. So there's lots and lots of galaxies. In fact, there's about 2 trillion galaxies we've counted so far. So there's plenty to go around, plenty for everybody. Here's an experiment you can do at home if you want to look at the Milky Way from Mars. That's something you could do there. But I thought I'd start perhaps by just measuring distances, because distances are just ridiculously big in astronomy. That's why we call them astronomically big. So the basic unit we start off is the astronomical unit, which is this. It's the distance between the Earth and the Sun, or at least the average distance, 93 million miles, 150 million kilometers. We hardly ever use this in our discipline. It's much too tiny. It's used within planetary science to measure distances to planets, but you know, we kind of almost never use that unless we're looking at tiny things in galaxies. Much more common are light years or parsecs, and light years are perhaps more commonly known. In astronomy, we tend to use parsecs. I don't really know why, but that seems to be the de facto measurement. But if you can think of 1 parsec is about the distance between stars. So it's about 4 light years to the nearest star, or just over a parsec. So stars are on the average are about 1 parsec apart. So that's kind of, you know, just gives you a feel for that. It's a ridiculously big distance, but that's the sort of distance you have to travel. So if you went at the speed of light, which we can't do in any sensible fashion, it would take you 4 years to get to the next star. And just to put that in context, this is based on Nottingham, but if you shrunk the sun down to the size of about a marble, so about a centimetre across or half an inch, then the next star would be somewhere on this circle here, so almost in Calais or up nearly in Scotland. So you can think of that as the galaxy we live in. You'd have one marble here, and the next marble you would come to would be across the channel or somewhere like that. So ridiculously big distances, and most of the galaxy is empty space, as you can see. Anyway, I better start by saying what a galaxy is. So lots of people have tried to work out what the galaxy is, and it's particularly difficult sitting inside the object trying to work out what it is when you can't stand back and get a nice picture. First person to try and do this was William Herschel in 1785, and he did this by perhaps the simple method of just pointing his telescope in different directions and sort of counting how many stars he could see. And the idea was that the more stars you could see, the further it extended in that direction. This didn't work out terribly well because he wasn't aware of a few things, principally things like gas and dust, which obscure our vision of the Milky Way that we live in. So he got a very distorted view. This is the view we think of where we live. This is the Milky Way galaxy as it would appear if you could move outside of it and view it from above. And this is where we live, in this little yellow circle. The sun is right inside that circle. In fact, pretty much all the stars you can see in the night sky with your naked eye are somewhere in that circle, almost all of them. So we get a very, very tiny view of the Milky Way. You can see it's much bigger extent. We're some way out from the center, about halfway out perhaps, in a very boring part of the galaxy. Not very much happening there, but that's where we live. And to go back to the measurements, it's about 100,000 light years across this galaxy. So, again, if you could travel at the speed of light, which is the fastest speed we know, it would take you 100,000 years to get from one side to the other. Or it's 30 kiloparsecs is also a distance. So kiloparsecs is sort of the units we use to measure galaxies. It's this many kiloparsecs. That's the sort of units we use. And has great reviews because there's 300 billion stars in the galaxy. So it's doing very well. But for a long time, we didn't really realize whether this was actually the entire universe. We could be sitting in this collection of stars and it could be absolutely everything we know about. If you look around the night sky, you occasionally find these clusters of fuzzy objects like this one here called the Perseus cluster. All these fuzzy things are, these like fuzzy orangey things are what we would now call galaxies. In the past, they were called nebulae because they weren't really sure what they were. And they are just scattered amongst the stars, so they could equally well be part of our galaxy. Here's another picture of another group. This is the Fornax cluster of galaxies, also scattered amongst the stars of the Milky Way. So unless you can sort of measure distances to them, it's very difficult to tell whether they are part of our structure or part of something else. And these are all just huge distances away. Even the stars are huge distances away, that it's very difficult to disentangle it. And it took Edwin Hubble, who the Hubble Space Telescope is named after, to sort of disentangle this. He managed to measure the distance to the nearest galaxy, and he didn't quite get it perfect, but using the instruments of the day, he got a reasonable measure. But it seems very clear. It was vastly beyond the furthest star that we could measure. So it was clear that these things were separate in their own entities. So galaxies are separate clusters of stars that just exist throughout the universe. And our Milky Way that we live in is just one of those, and not a particularly interesting one. Other than the fact that we're in it, there's lots more interesting ones, as we shall see. If you go up to the next unit, so we had kiloparsecs, which is 1,000 parsecs, measures sort of distances across galaxies. If you go up to the next one, which is the megaparsec, then that's the distance between galaxies. And you can go one bigger, which is the gigaparsec, and that's sort of when you get up to gigaparsec scales, which is we just think that's a billion parsecs, then that's we're getting towards the distance of the observable universe. So giga is about 1 billion. Well, it is exactly 1 billion. And so from that, you can also get the gigayear, which is 1 billion years. And 1 billion years is about the time anything interesting happens to a galaxy if you were watching it. So, there is watching paint dry and there's watching galaxies, and actually paint drying is much more interesting than galaxy evolution because it happens at a quicker pace. So with Edwin Hubble having found all these galaxies, we'd better do something with them. And it's a very common thing in science. If you don't know what to do, let's just make lists of things and see if we can make up any commonality between them. So that was tried back in the day with the animal and plant kingdoms. They started grouping things together, such as birds, insects, and fishes, and said, well, let's just put them all in the collections. This is sort of called stamp collecting. You put everything on the same page, and then later you try and work out, well, what's common between them and what's common across them. So you might well know that birds, fishes, amphibians, reptiles, and mammals all share roughly the same sort of structure of bones, and this led to the theory of evolution. So can we do something similar with galaxies? Well, the short answer is yes, we can. And it's a bit simpler with galaxies. There's less of them to less mixture of them, so you can do a little bit more with them. So Edwin Hubble set out to do this and said, could he categorize galaxies into different types? And he came up with a scheme that we still use today. It's not a great scheme, but it kind of works for us, and it's what we live with, and we all have to learn. So this is the scheme he came up with. He had 4 different groupings of galaxies. Down the left-hand side is the spiral galaxies. They look a bit like water going down a plug hole or something like that, but have a spiral structure to them. The second group is the elliptical galaxies, and spirals and ellipticals are by far the most common galaxies out there. But so if you find a new galaxy, it's probably going to be one of those two. The other 2 types he identified is this one over here. This is called a lenticular galaxy, and they're easier to explain after I've explained the first 2. And then, like any kind of good scientist, he had this idea that, well, if it doesn't fit into any of the others, I'll have a kind of bucket that I can throw anything that doesn't fit into. So he has the irregular galaxies over here. So that is kind of enough knowledge if you understand spiral, elliptical, and these other 2 lesser, the lenticular and the irregular galaxies. That's probably enough knowledge to get you through certainly parts of the second year exam at Nottingham on galaxies. So you could all be galaxy experts by the end of this talk. Some of the maths might be a bit more tricky, but you can at least identify galaxies. He produced this sort of scheme, which has been known ever since, which is called the tuning fork diagram, because it looks a bit like a tuning fork. So I guess tuning forks are less and less common these days. Much of it's now digital, but this is his description of it. So we have the ellipticals over here, categorized from E0 to E7, depending on exactly how elliptical they are. So E0 is pretty much circular, and E7 is very extended. The S0s, which I'll come back to, they're the lenticular galaxies. And then the spirals, and he split these into 2 types. So we have the spirals with a bar across the center, which is true of the Milky Way, and spirals without a bar across the center, which is true of some others. So that's the sort of thing we have to teach our undergraduates, and they have to learn and maybe draw in the exam. It does let you understand this galaxy joke. 3 SB galaxies walk into a pub. The landlord said, "Get out, you're all barred." So if we have a bar across the center, which you can see across here, that's the barred thing. Very weak joke, but anyway. Let's have a look at some galaxies so we can get a sense of what they really look like. This is our nearest neighbor. This is the Andromeda Galaxy. It's 2 million light years away. So you're seeing it as it was 2 million years ago. So yeah, if anybody's on there looking back at us, they're seeing us 2 million years ago. So probably nothing very interesting is happening to us from their point of view. It has the distinction of being the furthest object you can see with the naked eye. If you know where to look and you have a very dark sky and your eyesight is reasonable. I have to say my eyesight is probably not reasonable enough to see this. I've had a few goes. I can see it in binoculars, small telescope, but it's a bit iffy as whether I can actually see it with my naked eye. Some of you may be better. It does look big and magnificent, and you thought, well, you know, surely I can see this object, but you probably won't. It's quite a big object. This is it next to the full moon, so you can see it extends quite a way across the sky. But if you actually go out and look for it, this is what it looks like. There is this faint wispy cloud that you're not really sure whether you see or not. It doesn't even look as good as it does in this picture. It's you know, a very faint object, but it is, you know, if you can see it, you are seeing 2 million light years away. So that's our nearest neighbor, the Andromeda Galaxy. And we'll be having more to do with that in our future, all of our futures. This is another spiral galaxy, but this time edge on. So we're seeing one here. This is called the Sombrero Galaxy. Apparently looks like a Mexican sombrero. You can see a lot of the light here, but you can also see a lot of this dust that I briefly mentioned. This is dust generated by stars, this black stuff here. It's not really like household dust. It's a bit more like smoke in its very fine particles that absorb light nonetheless. So that's the Sombrero Galaxy. This is one of those barred galaxies, as you can see, very stretched out, this big bar across the center, and these long spiral arms going out. Another feature you can see in this, there's a color difference. Towards the center, it's a sort of more reddish orangey color, and out towards the spiral arms themselves, they're a very blue in color. That gives us some of the first clues to what's going on in the galaxy, which we'll come back to in a couple of slides' time. So that's going to let us know exactly what's going on in the galaxy. If we're going to describe a spiral galaxy, then a fried egg is an excellent stand-in for that. It has this big yolk in the center and a flat white disc-like shape, but that is where we live, somewhere out in the white area. And if you've still got CDs or DVDs around, then that is almost a perfect example for how the scale is. So the width of the CD to the thickness is just about right. So spiral galaxies are very thin compared to their width. Say 100,000 light years across, 100,000 years to cross it, but probably only a few thousand to go up across the width or the depth of it. When we talk about them, we talk about this bulge bit in the center. Most spiral galaxies have a bulge, not all of them, but most of them do. The disk, which is where we live, and then there's a halo around which contains a few objects, things called globular clusters, and a few stars are also orbiting in that. But it's kind of like the flotsam from the galaxy. Most of it is within the bulge in the disk, and this is a very rarefied halo of bits and pieces. But we also sit in something much bigger, which is called the dark matter halo. We don't know what dark matter is. We've got an idea how it works. We depend on it for a lot of our calculations, but we don't know really what it is. I have a whole hour's talk on what we think it might be, but you can summarize it in one sentence with no idea what it is. But we believe it exists, and it's about 10 times bigger than the galaxy. So we sit in this big dark matter halo. Here's another spiral galaxy, somewhat inclined to us. This one doesn't have a bar across it. You can see it just has this center. Again, you can see there's a difference in color between the outer and the inner. This one is taken through, I think, probably an infrared filter. Here's a galaxy you can make at home. This is particularly good after Christmas when you don't know what to do with all those sweets left over. And here's another picture of yet another spiral galaxy. This one is called a flocculent spiral because it has lots and lots of arms. Flocculent is, I think, comes from like wool, puffed up wool, something like that. But again, you can see quite a difference here. It's very red in the center, very blue on the outside. So let's dive into that and explain what's going on in that. For that, you need to know a little bit about stellar evolution. So I'm going to cover stellar evolution in one slide. So you're going to be experts on galaxy and stellar evolution by the end of this. 2 for the price of 1. So stars and their colors. Let's start with the sun because that's most familiar. The sun looks a sort of yellowy whitish color. It's about 6,000 degrees on its surface, centigrade, but it doesn't really matter, and weighs 1 solar mass by definition. We weigh all stars by comparison with our own sun. So it looks kind of a yellowy color. But there are other types of star around. There's those that are smaller, called a red dwarf. This is about half the size of the sun in mass, and a lot cooler at 3,500 degrees. And it appears very red in color. This is because it's not quite got up to the heat of the sun. So, like a blacksmith working iron, you see it as he works the iron, it gets hotter and hotter, and it starts off black maybe, that gradually gets to an orangey color, going through red and then orange and then to a bright white color when it gets really, really hot. Same is true of stars. They get sort of brighter as they go up in temperature. So red dwarfs give off much more of their energy in the red part of the spectrum. The sun towards the middle of the spectrum, so gives off a bit of everything. When you get to really big stars, which we call like a blue giant, they give off most of their energy in the blue part of the spectrum, which is very energetic and even into hotter. So the ultraviolet, which we can't see directly. But anyway, they are much bigger. They might be 30 times the mass of the sun and 30,000 degrees on the surface. So that's kind of why they give out so much energy in this the blue part of the spectrum. They're giving out lots in the red and the yellow, but most of it's coming out in the blue, so that kind of tends to dominate. So those are the different kinds of star, but they each live for a different period. So the sun lasts for about 10 billion years, 10 gigayears. We're about halfway through, so we've got another 5 billion years left in the sun. Red dwarfs burn their fuel very, very slowly, very economically, so they maybe last for 100 gigayears. Blue giants, though, very, very fast. They just burn through their fuel as quickly as they can. They only last for a few million years. So 20 to 30 million years is typical for a blue giant. Sounds like a long time to you and me, but on cosmic scales, it's very short. It's 60 million years ago to the dinosaurs ruling the Earth. So we could have had 2 blue giants born, live and die in that time. So very quickly, quick turnover of blue giants. So going back to the galaxy, what we're seeing in these arms are all these blue giants. These are very, very bright stars, very hot, give off a lot of light because they're so big and so luminous. But I've just said they don't last very long. And here we are looking at a galaxy which is billions of years old. In the center, we're seeing very old stars, but around the outskirts, we're seeing very new stars because they keep being born. Having new stars born at a certain rate. In the Milky Way, we have about 1 new star born every year on average. They take millions of years to actually go through their birthing process, but it's about, on average, 1 new star pops into existence in the Milky Way every year. And the same is true of most of these galaxies here. So we're seeing lots of new stars born. Most of the new stars born are stars like the sun or smaller, but there's a few of these very bright blue stars that keep being born and turn over. They will explode and disappear after a few million years, but they will be replaced by other new stars. So that tells us a bit about the science here, what's going on. Here's another nice spiral galaxy. Again, you can see the blue and the red picked out in this case with different filters. But one other feature of a spiral galaxy is they are very ordered and very methodical. All the stars are going around in approximately the same path. So they're all going around a nice, steady flow, going around once, in the case of the Milky Way, about 250 million years to go once round. So that's nice and ordered. Everybody's going around. There are a few, oddities that don't follow the flow, but by and large, everything is going around in a very nice, orderly fashion. So this is in contrast to the next series of galaxies we're going to look at, which are much less interesting, much less beautiful. These are the elliptical galaxies. So these are sort of a hazy galaxy. You can see they're sort of brighter in the center, but much fuzzier as they get to the edge. And these are true sort of, whilst the spiral galaxies you could describe as like a CD, very flat structure, these are very three-dimensional. So you could think of these more as rugby balls or soccer balls. They have a complete 3D structure to them. And not only that, but they're going around in all sorts of directions. So the stars are not just going around all together, they're going around, they're all orbiting the center of the galaxy, but they're going around in all sorts of directions. There is no single direction, they're all going around. It's a much more chaotic thing. So we can't make as many measurements with this. You can't say, what's the average speed of the stars going around? They're just doing whatever they feel like. This is an E5 galaxy, so this is one that's slightly stretched in its dimensions. And here's a nice E0, so this is a very spherical one, be much like a football, very round in a sphere-like structure. And this one's an E7. This is as stretched as they get, being pulled out into a very long, elongated structure, partly because of this other galaxy you can see down to the bottom right here that's having some gravitational influence on that. So, yep, that's the elliptical galaxies. Then we come back to the other ones that Hubble defined, which are these lenticular galaxies. Lenticular from lens-like, I think, you go far back in etymology. And these are very much the dimensions of a spiral galaxy, but they have the color constraints of elliptical galaxies. Oh, I should have said, if you just jump back to elliptical galaxies, you can see there's very little blue in these galaxies at all. Nearly all the stars are red. So elliptical galaxies are really stopped forming stars. They are just happy with the stars they've got, and they're not going to make any more. They're just going to coast along. So there are none of these new bright blue stars being made. They're just these old red stars that are just keeping going. So the same is true of the lenticular. These are also full of old red stars, and they're again not doing very much. But I said they're very flat. And you can think of these as a spiral galaxy that's stopped forming new stars. So we're no longer getting these bright blue stars that are picking out the spiral arms of it, and we're just getting a flat disk that's just evolving. So they've kind of just got as far as they can and are not really doing anything new. That's 3 of the 4, and the 4th is the irregular, which is anything that doesn't fit into that. So this is an irregular. This is a nearby irregular galaxy called M82. Anything with an M in was found in the 1700s by Messier. And so they're all kind of bright nearby things. So this is an irregular galaxy. You can see it doesn't really look like anything there. It looks like a bit of a mess. And this one is also called a starburst because it has a lot of these blue areas in it where it's forming lots and lots of new stars. In this case, it's way ahead of us. It's probably forming 200, 300, 400 stars a year out of this. because something is happening to this galaxy. There's this big outflow of material and stuff is just going on, and that's generating lots and lots of new stars. But if we come back in about a gigayear, this will probably have settled down into being an elliptical galaxy with no new stars being formed. There's this big burst happening at the moment, but it probably won't continue. We also get dwarf galaxies. These are just a few 100 million stars within a galaxy. And these often form around, well, they're usually hanging around other much bigger galaxies, such as our own. And because they are orbiting these bigger galaxies, they never really get the chance to settle down and form what they would like to form, because they're always being tugged around by the gravity of the much bigger galaxy. So that's it. You have all the knowledge you need to know about galaxies now, the four main categories. You sit around and if somebody brings up a picture, you probably have a fairly good guess as to what it is. But luckily, there's a bit more to tell you about, otherwise I would finish here. But that is the main categorization. But after this was settled and everybody was happy with this, people started to find a few anomalies. And one of these was a category called active galaxies. Active galaxies happen both for elliptical and spiral galaxies. And the first one or two were found by American astronomer in the 1940s called Carl Seifert. So they're called Seifert galaxies. Here's a nearby one. It looks like a spiral galaxy, and indeed it is. But what characterizes this as special is the center of it is very, very bright, much brighter than it should be, much stronger luminosity coming from it than would be expected. So Carl found this particular galaxy and a handful of others and published a paper on it saying there's something odd about these. The center of them is much brighter than they should be, and they got to be called Seifert galaxies as a result of that. As we got better at with telescopes and examining things, we started to find other cases of these. Here is another active galaxy. This is Hercules A. This is this blobby thing here, a couple of stars beside it. This had a very bright center to it again, but as we got better with telescopes, we could move into other wave bands. So this is just visible light here. But if you look at it in the radio waves, such as you might discover from places like Jodrell Bank and similar, you can see there's more to it than that. This is a radio picture overlaid, and you can see, you know, the nice visible bit here, which you'd see through an optical telescope. But out here is vast quantities of gas that are being shot out of this galaxy at prodigious rates and for a very long time. If we think back to the Milky Way, this galaxy is probably bigger than the Milky Way, but you know, just the Milky Way, it takes 100,000 years to cross this at the speed of light. So to erupt these big structures out into space, you know, this is many times bigger than the galaxy itself, so it must have been doing this for millions and millions of years. That takes a very powerful force to do that, because you're shooting this out against the gravity of millions and millions of stars. And why isn't it all falling back? It's because it's being shot out at such a rate that it's beyond the escape velocity of the galaxy. So that's a very powerful source to do that. So we found some others. Here's another one, Centaurus A. You can see again this big cloud of stuff being shot out from the middle. So that was another one. Then we just started to discover other types of things. There's a big history to these. These are called quasars, and they were originally thought to be stars because in the left-hand picture you can see it looks very like a star. But when we got to measuring how far away they were, they appeared to be like halfway across the universe. So they're very bright objects. And on the right-hand side, we've got a picture of a similar one taken with Hubble, where they managed to blot out this bright center, and you can see there's a fully galaxy behind it. And these do turn out to be galaxies too, with a very bright center. So those are called quasars. Bit of a mystery for a while they were too. Even brighter were things called blazars. and found a few of those things too. And it all started to get very complicated. We had Seyferts. There were several types of Seyfert galaxies. Then there was quasars, there was blazars, there was other radio galaxies that had very bright centers to them. So it all got a bit messy, and we thought we got lots and lots of different types of galaxies. But it turns out they all have a common underlying cause, and that makes things a lot easier to learn, particularly if you're doing an examine, if I have to say. So the culprit is this. This is the very center of all the galaxies we've looked at in any detail. They all have a very, very big black hole at the center. So black holes come in two sorts. We have stellar black holes, which are formed from stars, and usually weigh somewhere around what a star weighs, usually a few times more. And they might be 10, 20, 50 times the mass of the sun, these stellar black holes. But then we have another type called the supermassive black hole, which sits at the center of a galaxy. And they weigh anywhere from 1 million to a billion times the mass of the sun. And we really don't know how you make one of those. We don't have a good theory for that at the moment, but they seem to exist. We've taken pictures of them. This is a picture of a nearby one, or at least the shadow of it. You can't really take a picture of something black on a black background, but we can see some of the shadowy parts of that. Anyway, it turns out these are a very good mechanism for making this powerful thing from the center of the galaxy. And this formed from this. This is our picture of the very center of the galaxy, including our own. You have this black hole, which isn't very big. It's about the size of our solar system, perhaps. Then it's shrouded by a ring of debris material that's spiraling around it, in the case of these active galaxies. In the case of our own galaxy, we do have a supermassive black hole, but it's not active. It is not consuming anything. It's eaten everything nearby, so it's now gone very quiet. But anyway, this lets you explain most of these things. If sometimes they have jets shooting out of them like this, which we saw in the previous ones. They seem to be somewhat transient, and they perhaps only last for a few 100 million years or 50 million years or something like that, and then switch off. So we can then explain most of these galaxies by just looking at how we can see them on the night sky. So a Seyfert galaxy, in fact there's two types, the Seyfert type 1 and 2, depends on whether you're looking across the ring of debris or whether you can look almost into the heart of the black hole, which you can't see, it's far too tiny to see, but that just gives you a different picture of it. Similarly, if it does have one of these jets, then this would be a quasar. You're looking down almost at the jet. You're seeing quite into the heart of the galaxy at this point. For a blazar, you're looking straight down the jet, so that's why they seem to be very bright. You're actually looking straight into the beam of it. And then you get these various other ones which you can see at different angles. So that makes things a lot simpler, certainly for students trying to explain these things in exams. We've also noticed that the night sky isn't static. It does take millions, billions of years for anything to happen, but things can happen. So galaxies can collide over a very long time. So here are two galaxies that are in the process of colliding. You can see already there is some connection between these two galaxies, and they're coming closer together. This is a galaxy a bit further on in the process. See, perhaps here is the original galaxy, and here is a new one coming in. They're crashing into each other. They would certainly be, this looks like it was originally a spiral galaxy, but they are well on their way to forming an irregular galaxy at this point. Things are getting very stirred up. You're getting lots and lots of new stars being formed. So there's lots and lots of this blue stuff happening where they're forming, but it's going to settle down in days to come to perhaps elliptical galaxy. Then there's a whole lot of oddities that I couldn't really fit in anywhere else, but I thought might be interesting to see. So the very largest galaxy we've ever seen is not this one. This is a spiral galaxy for comparison. If we shrink that down to about this size, this is the very biggest galaxy we've seen. It's an elliptical galaxy and has the catchy name of IC 1101. So that's the biggest galaxy we've come across so far. This one we've nicknamed the Darth Vader galaxy because it looks a bit like Darth Vader's spaceship. And we also have the lightsaber galaxy, which looks a bit like a lightsaber over there. Now, this used to be the furthest galaxy we've ever seen. This is, again, casually named GNZ11, which is a redshift of 11. But that puts it about 13.4 billion light years away. So this is almost to the edge of the visible universe. The edge of the universe is about 13.8 billion light years. So this is very, very early on. But as was mentioned in the introduction, that the James Webb Space Telescope is now improving things. And since this was the record holder for quite a while, but since that's been launched, we've now got new contenders. This one here, 13.5 billion light years away. And there's another one here called HD1, which we're not quite sure yet. We need more data, but it's probably somewhere between 13.2 and 13.5 billion light years away. HD1, much simpler to remember. This is a ring galaxy. It seems to be a sort of elliptical galaxy, spiral galaxy rather, with the center blown out of it. We don't really know how you make one of those. We don't have a good theory for it. There's a few papers on that, but they're very, very rare, so we don't worry about it too much. We also have things called, this is a BCG, which is the brightest cluster galaxy. Galaxies usually form, or quite often form, in big clusters. So there's more than one galaxy in a cluster. Tens to hundreds if we call it a group, and the clusters usually have 100 galaxies upwards, up to thousands in some cases. And the very biggest galaxy in that is called the BCG, the brightest cluster galaxy. Now, this is a nice word. It's time to talk about lurgs, U-lurgs, and E-lurgs. And astronomers being very bad at coming up with illustrative names, they just go for the simplest name they can think of. So these are lurgs, or this is a lurg here. So this is a luminous infrared galaxies, LIRG. So this is a galaxy that is not very interesting in the visible spectrum, but if you're looking in the infrared with an infrared telescope, they are extremely bright objects. So luminous infrared galaxy, great. So, or lurgs for short. And then they found a class of things that were much brighter. They seem to have the same characteristics, but much, much brighter. So they became the U-lurgs, or ultra-luminous infrared galaxy. So we have the U-lurgs. But then you can see a progression that they found something that's even more brighter, maybe 10 to 100 times brighter. So they became the extremely luminous infrared galaxy, E-lurgs. And it's just as well we haven't found any really much brighter than this, because we're struggling for adjectives at this point, or at least clean adjectives that you can print. People have suggested other adjectives that you could apply to the beginning of that. So E-lurgs, or lurgs in general, great thing to drop into the conversation. Now this is where I do most of my research, is in simulations, because you needn't be good, you can just simulate things. So a lot of my colleagues use bigger and bigger telescopes like this one. This is one of the biggest ones being built that we might come back to at the end. So really big telescopes are a great way of exploring the universe. Or you can go to mathematics and you can explore the characteristics of the universe by getting to more and more complicated mathematics. And we for better or worse, we share our department with the particle theory group, who work on sort of cosmology descriptions of how the universe came apart and what makes it up, and theories of how universes have come and go. And they have seminars every Friday that you can go along to, where they discuss the latest in things. And I've learned not to go to these unless it's a particularly interesting subject or one I can understand. Because here is a typical abstract from one of their seminars, and it's full of words that on their own I can sort of understand, but when you put them into a sentence, it just becomes just word salad. You know, I can't make any sense out of this whatsoever, one way or the other. Maybe some of you can, and you can perhaps explain it to me. So I've learned if you go to one of these things and you can't even understand the title, things never get any better, and you leave with a thudding headache and desperate need for paracetamol or something. So instead, I work with simulations, and for those you just need really big computers, and you come up with a program and you throw it on the computer and you let the computer do the hard work, and then you come up with results. And this is pretty simple stuff. We just use Newton's law of gravitation. We don't even need to go to Einstein's theory for this, because this is plenty good enough. It's quite a simple formula to solve. The trouble is these green blobs of the particles, we solve it on for representations of the universe. But to do a decent simulation of the universe these days, you need somewhere above 1 billion to 1 trillion particles. So you have to do the calculations on all these particles. So you have to do 1 trillion particles. And then once you've done it, you move all the particles based on the forces, and then you redo the calculations. So you can see it's just a big mathematical exercise. We're helped in this somewhat by this dark matter that I mentioned earlier, that we think surrounds every galaxy and actually dominates it. So if you look at the constituents of the universe, this yellowy bluey bit here, which is gas and other stuff, that's the bit we've understood and researched for the past several hundred years. And then we quickly discovered, certainly towards the 1980s, that actually dark matter, this stuff over here, which we don't really understand, outweighs regular matter by about 5 to 1. And they're both overshadowed by this thing called dark energy, which we know even less about. We didn't really even come across this until the early 2000s. That dwarfs everything, but luckily this doesn't have huge influence on the universe, so you can do your simulations with much of this. And this is what we try and get to. This is a picture of the universe, where for every galaxy we've charted, we put down just a dot on this picture. So we're sitting right at the center here. This is us looking above the Milky Way and below the Milky Way. We can't really see into the Milky Way or out of the Milky Way because our view is largely blocked by stars and other things. So we tend to look above and below and just see what the universe looks like by putting a dot for every star and its distance away from us. So this is the sort of simulation we run, and we're getting quite good at these. This is a simulation I ran on the local high-performance computer at Nottingham, and you can see clouds of gas and stuff that all come together. And we call this the cosmic web because it looks a bit like a spider's web and groups stuff together. And it evolves over time. And if we just take a snapshot of this, this is one from the simulation. This bit here with the yellowy stuff, this is where there's a large density of galaxies, lots and lots of galaxies. This is one of those galaxy clusters where there might be thousands of galaxies all spinning around each other, going around in some sort of convoluted way. Right out here in this very backwatery bit, this is where we would live. This is a very sparsely populated area with only a small number of galaxies. There's only really 2 big galaxies in our area, ourselves and the Andromeda, and nothing else of interest until you get many millions of parsecs away. But anyway, we got quite good at doing these simulations, and this is one that was done a while back now. The stuff in blue is the real universe as observed by astronomers, putting again dots down for every galaxy they can see, and the stuff in red is from a simulation. And though obviously not identical to each other, we're getting the broad structure correct. there is this big wall of galaxies you can see along here called the Sloan Wall, and we get something similar in these simulations here. You get these big areas with nothing much in, which we call voids, and you get similar things in these simulations. So those we're getting almost correct. There's still little ways to go, a bit more physics to be understood, but we can go a long way with that. And in fact, we can go far enough to predict our own future. And this is a simulation of our own local area. So this is the Milky Way spinning on its axis. And you can see what's in the neighborhood. So there's the Andromeda galaxy there. And there's a much smaller triangulum galaxy, M33. And this is just predicting the future. So you can see the time ticking away in gigayears there, billions of years. So at about 4 billion years, the Andromeda galaxy is going to be a lot closer to us than it is now. And in fact, it's going to collide with us and make a complete mess of everything. So about 4 billion years, we get a complete mess, and then we come back together. We're gravitationally locked in this sort of dance together, and we smash into each other backwards and forwards a few times, and then we end up, although we started with two really nice spiral galaxies with nice colors and everything, you end up with this rather messy elliptical galaxy that has none of this nice color and is just a bit of a train wreck at this point. So that's a good date to put in your diaries. About 4 billion years from now, be somewhere else, because it's going to get a bit messy. 4 billion years is also about the time our sun starts to expand and explode. So it's also a good time to leave our solar system. So 4 billion years, yeah, good time to go away. So let me just wrap up with a few things. There's still some open questions to examine. So there's still work for us to do as astronomers. These supermassive black holes, we keep finding them. They seem to have a strong influence in galaxies, but we've no idea how you make one of those. There's all sorts of reasons why we don't understand that, but we'd like reasons why they appear, because they appear to evolve very, very quickly. They seem to appear very quickly into even very early galaxies. So that's something we've got to look at. Another one, we've got 2 or 3 PhD students at Nottingham looking at. If you just sort of plot a rough graph of where these galaxies exist, with mass of the galaxy along the bottom and color up the top, get this cloud of blue galaxies, which are by and large the spiral galaxies here, and then the red sequence, which is all the ellipticals. But you can see they don't really overlap, and red galaxies are much heavier than blue galaxies. So is it a question that they get bigger and then they turn red, or is it they turn red and they get bigger? We're not really sure of that. And there's this bit of the galaxy, bit of the graph called Green Valley, where we look at things. Another idea is to revise Hubble's tuning fork diagram, because maybe there are better ways to describe things. So people have suggested this, which is the comb model, which you have the rotation of the galaxy along the bottom and then spiralness going up the side. So this is perhaps a better scientific, more accurate description, but at this point, I really don't think we're going to overturn Hubble's tuning fork diagram. Everybody learns it. So, it's a brave effort to come up with a brand new way of describing things, but they're not going to happen. How are we going to get forward to the future? One way is to use new techniques. So this is a satellite called Gaia, which has been mapping the Milky Way in extreme accuracy. So getting like a GPS system for the galaxy. And using that, you can do lots of things. So this is one of their press releases. They looked at all the stars in the Milky Way, and they found, this is the Milky Way as seen from Gaia, and they found some of them, these yellow ones, are moving at extreme speeds. So these are going far too fast to actually stay within the galaxy. So they're going to go shooting out of the galaxy and off into intergalactic space in the near future. They might be just passing through. They might have come from some other place, or there might have been some reason they've been kicked out of our own galaxy. So you might have a talk about the James Webb Space Telescope. That's providing us lots of new information and overturning in some minor ways some of our theories and giving us new data to work with. So that's certainly something people are scrabbling to get data from. There's also these new telescopes. So with our bad past of naming things, these are some of the current biggest telescopes in the middle here, called the Very Large Telescopes, or VLTs. The new one being built is the ELT, the Extremely Large Telescope, being built in Chile. Has a mirror of about 40 meters across. So this collecting area of light is about half a football pitch. And if you want to know how big that looks like, that's it laid out in cardboard. So these are the sort of tools we're going to use to get forward to tomorrow to do some more research. So I'm going to leave you with just a few conclusions from this. Galaxies are really big. So our own galaxy has about 400 billion stars in it. That's enough stars for every person living on Earth to have 10 to 100 stars each to call their own. And probably each of those stars has a number of planets around it. So, there's room for everybody to have their own private Eden or whatever they can construct. Most of those stars are probably not good places to live on. Most of the planets are also nothing like Earth, but there's room for expansion. But if that's not enough, there's about 2 trillion of the galaxies around. Not all of them are spirals like ours, but are perhaps better places to live. Some of them, quite a lot of them, are ellipticals. But there's more than enough galaxies for everybody to have, maybe 1,000 to 1,000,000 galaxies each. Some of them may be occupied by aliens, I don't know. So you may not get first dibs on every galaxy you pick, but there's plenty to choose from. Research continues, including at our own department, but new telescopes, new tools always give us new insights into to new structures, let us solve problems that we know about, but overturn problems that we didn't know about that we now know need to solve. So with that, thank you very much for listening. I hope you found some of that informative, and you can now go and bore all your friends with details about galaxies. So thank you very much for listening. And if you've got any burning questions, I could certainly try answering them. So over to you. Thank you.
Lovely. Thanks, Julian. That was brilliant. Beautiful stuff. Absolutely fantastic. Do you want to stop the sharing so that we can see things now? I think everybody knows how. Does anybody not know how to, on the reactions button, how to raise their hand if they want to ask a question, or is everybody happy with that? And if so, those who are burning to ask questions, it's already starting. So raise your hand and we'll take it through that way. There was one in the chat, but perhaps we can come back to that or put it up as a verbal one, whichever is easiest. So
yeah, whatever works. Yeah.
Okay. Right. Malcolm Fowles. Lovely. Malcolm.
Hello. I'm mystified as to why you didn't draw a connection between the blue and red cloud diagram and your simulation, in which 2 rather blue spirals turned into a large red elliptical, Andromeda and the Milky Way. So, I'm just, presumably it's a lot more complicated than that. So can you comment on?
Yeah, in some respects it is. Most of the galaxies seem to either fit in the red or the blue cloud. There's very few we can find that are in this thing called the Green Valley. So they seem to transition between one of these things, if indeed they do. Not everybody agrees on that. But if they do, they seem to go across very quickly. So it's a question of catching them at it, or indeed, as you suggested, perhaps have a simulation. Now, the simulation is perhaps a little too simplistic. It shows probably what happens with our two galaxies, but there are ways of forming, elliptical galaxies don't have to form by two spiral galaxies crashing into each other. They can form just of their own volition if the circumstances are right, we're fairly sure. You can also, in some slightly extreme situations, you can get an elliptical that will turn into a spiral. The elliptical sort of is the center of it, and then it gets a big spiral gas that flows in from somewhere and forms a flat disk. And then, so you can get them sort of going backwards and forwards between each other. So there's various of these theories, and it's really getting enough examples from that the universe was willing to give us to explain what is the dominant way, or is this just a very odd thing that's happening? We can have these theories, but it's always good to have data to back them up with. Yes, a very insightful question. Thank you.
Lovely. Paul. Paul M.
Hello, I had two questions, but I think you've just answered the second question about spiral galaxies turning possibly into elliptical galaxies according to the collision that you show between Andromeda and the Milky Way, and I think you answered that one. The first question was why it struck me that it was a little bit odd that you said that it was really dark matter and material matter that featured in the evolution and general nature of the cosmic web and the way you use it in computer simulations. And I wondered, you said dark energy, I think you said that dark energy really didn't come into it. And I just wondered, seeing dark energy is supposed to comprise, what, 3/4 of the sort of energy, whatever you like to call it, in the universe, then why dark energy isn't more prominent in the evolution of the cosmic web? I don't know whether that's a reasonable question or not.
Oh, that's an extremely reasonable question. Thank you for bringing that up. Yes, very insightful. So there's a couple of things going on here. So regular matter and dark matter, we believe, sort of work in the same way, in that they're particles and they have gravity that pulls them together. It doesn't work quite as well with dark matter for various reasons I could explain about, but so they tend to settle down and clump together and form structures. So that in fact, with the evolution, the dark matter forms first because there's more of it. So it makes a big sort of gravity well, which tends to suck in regular matter. And then you get the stars and the galaxies that form from that. Dark energy, as far as we understand it, which is not very much, I have to say, seems to be a thing that's pervasive across the entire universe. It's like a property of space. And so the more space you have, the more dark energy you get. So as the universe is expanding, we're getting more and more dark energy. And it seems to manifest itself as a very weak repulsive force. So it pushes things apart. But as the universe gets bigger and there gets more of this, it's starting to push things apart even faster. But there's dark energy pushing you and me apart, or pushing everything apart. But it's so weak that gravity dominates it by a huge amount. So even between the Milky Way and the Andromeda, the gravity, which is a very weak force, it has to be said, is still far dominant over the dark energy that's trying to push the two apart. So gravity easily wins on that one. But when you get enough empty space, dark energy starts to take over and can start to push things apart. So yeah, that's at least as much as we understand about it right now. It's this weird force. Nobody knows really anything about it. Nobody has very coherent theories about it at this point, except we see its effect, and it tends to be a repulsive effect.
Sorry, I have if I'm not interrupting anyone else's question, I have a quick supplementary one to that.
Yeah. As
far as dark energy goes, and I think it might stray a little bit outside your talk, but only in terms of, I thought energy was one of the fundamental things that in terms of conservation laws, that you tended to get energy conserved within any particular system. And it just seems rather odd to me that you just mentioned in your answer that you have this sort of creation of more and more dark energy. And so I don't know
Where's it
what
coming from?
extent you can use conservation to in explaining, I don't know, dynamical systems when you have this dark energy being created everywhere.
Yeah, that's an excellent question, and probably one I can't answer right off the head. But so I know people have looked into this, and some people just say, well, conservation of energy doesn't work in the entire universe. When you're talking about universes, that maybe it's getting it from somewhere else. Other people will answer it and say, well, it's sort of gravity winding down, and I don't think we have a good answer for that at the moment, or at least not one I can tell you. So if you go to the theoretical theorists, these sort of people that I gave the seminar outline from, they might be able to give you a much better answer to that. But I don't think I'm going to admit my ignorance at this point and say I don't know where the energy comes from.
Thanks very much. Anyway, for a very interesting talk. Thank you.
Thanks, Paul. Yeah, Christopher. Christopher, you haven't unmuted yourself.
Yes. Yes. Hello, Julian. Just a question. I hope it's not a foolish one. I came across something the other day called the Great Attractor, which shows all the galaxies, if you like, in a cone, all heading towards a single unity.
Mm-hmm.
Have you a comment on that?
Yeah, I mean, yes, this is kind of well known. It's a local phenomenon around our area of space. If you can talk about millions of parsecs as local, but it seems to be the cluster of. So we belong to our local group, which is just us and Andromeda. We are loosely associated with, I think it's the Perseus cluster, which is a much bigger grouping called a supergroup that has its own little cluster, but is gravitationally attracted to lots of other clusters around it. And it seems to be the heart of that cluster that, it's kind of the center of all the gravity around that. That is, things are being generally dragged towards. So we think it's just, like you saw with Andromeda and the Milky Way coming together, we're probably all going to, over billions and billions of years this time, we're all going to gradually move towards this more central point that is kind of the gravitational center of everything around us.
So a supplementary there. So could this actually be the Big Bounce?
Big bounce? No, don't think so. We think it's just. Okay. Once it was originally discovered, there was lots of sort of conspiracy theories. We all get sucked into this place. Is it a hole in our universe that we're going to go through? But it seems to have a much more prosaic reason. It's just kind of the center of the mass to everywhere around us. I don't think it's solidly nailed down at this point, but that seems to be the general view. Yeah, you might be right that there is more to it than this, but I think I'm going to go with the standard answer that it's just the sort of local density that we're headed towards.
Thank you.
Thanks, Chris, and thanks, Julian. So, John. Or John. Yeah.
Yes. If I were a long-lived alien living somewhere in the Milky Way 4 billion years from now, what would I experience when the two galaxies come together? Can you sort of provide a little bit of a movie of what would go on? Because I mean, it is still, a galaxy is still very largely empty space. And I suppose a few physical objects, hard objects, might clunk into one another. But I can imagine that an awful lot of people, aliens, might not even notice.
Yeah, that's a very good question and a very good scenario. So as you say, they are mostly empty space. We generally, certainly in simulations, we treat them as non-interacting. So they would just pass through each other. And that is generally what we believe will happen when Andromeda and the Milky Way collide. There won't really be any collisions of stars. You might get the odd one bump into another one, but most of them will just pass through each other. What is more sticky is there's big clouds of hydrogen gas that are floating around that might get turned into stars at some point, but they will collide with each other. So you'll get these big gas clouds that will collide. That may well trigger lots of star formation. So when we're in the middle of this sort of event, there might be lots and lots of new stars being born. Some of these big bright blue stars. So we might well see something like that starburst galaxy happening. It's debatable whether we'll see Andromeda any brighter as it comes towards us, because as it gets closer, it also gets bigger. So you're sort of spreading out the light. So that's something we sometimes argue about in the department. Will you actually see this thing coming, looming towards us, or will it just because it's spread out or similar thing? What might do for us though is that as these things pass through each other, they probably won't collide, but you'll get a lot of gravity dragging things around. So we have this thing called the Oort cloud, which is this big sort of layer of debris on the far outskirts of the solar system, where we occasionally get comets that come into us and pass by us from. We don't get very many of them, but when you get something like this plowing through and you get lots of stars getting nearby, that may well get distorted and we may get a big rain of comets. And you may know that a really big comet or asteroid did for the dinosaurs, that kind of destroyed the dinosaur ecosystem. So that might well do for anybody still living on Earth at that point. Yeah, it's probably worth watching it from afar, I think, rather than being quite close up. And
thank you.
Okay, don't be shy about asking questions. It's unusual.
Just out of interest there, how big would the sun be at that point, though, in 4 billion years' time?
It will just about be getting into what's called its red giant phase. So that slowly gets bigger and bigger as it's not an instantaneous thing, but it swells up until we reckon it probably gets to about the orbit of the Earth. So we would be orbiting in the Earth right in the outer layers of this red giant sun at that point, which would be pretty toasty. It wouldn't be as hot as it is today. It might be only 1,000 degrees or something right on the edge and very wispy, but nonetheless probably not somewhere you want to be.
We'd be toast at that point, wouldn't we? The water wouldn't stand a chance.
Yeah,
of being,
the water would have long gone. Yeah.
Yeah, I think it's bad news.
Yeah, I should pack a flask of chilled water for that day.
Yeah. Val?
Yes,
Thanks,
quick question, Julian. That was fantastic visual. But what is it, the black hole that makes them spin? Because you also included a few oddities which were chaotic. I know chaos theory is sort of part of physics and all the rest of it, but can you say anything about that? What
Sure.
propels them? That's really the question. Thank you.
Right. Yeah, no, that's a really good question. And yeah, very, very, very prescient. So it's not really the black hole that spins. The black hole, although we call them supermassive and they are really big, they are on the scale of the galaxy. They're very tiny in volume. I say they're about one solar system across. In fact, the one in the center of our galaxy could easily fit within Mercury's orbit. So you could actually replace the sun with a black hole and we could still happily orbit it. So they are very, very heavy, but there are maybe 100,000th the weight of the entire galaxy. So again, they're not a huge factor on that. But they nevertheless, as you say, they do have a serious impact on the galaxy, and there are some interesting relationships between the black hole and the galaxy. But as to spinning, it's actually just their formation. So it's very unusual for everything just to fall in a sort of straight form, everything to come. They usually fall in and then they sort of curl round like this.
Right. So are the oddities coming or are they going then? Are they forming a galaxy, spiral one, say, or are they like the star one, that the star, is it coming out? Is it disappearing? Or
No,
going?
they're sort of all in orbits going around, but
Yeah.
it's a bit like, you know, going back to the bath plug thing. If you pull the bath plug out, the water might all just pour down straight, but it never really does it? It always spirals around.
Yeah.
That's because
So,
any
I mean-
small movement is amplified as you get closer, and it gets, you know, into a more clear spiral shape. So everything just orbits around like that. So in the ellipticals, they're just coming in from all angles. So they're all going
Okay.
around whichever way they happen to come in.
So one more. So by what I understand by that, there is perhaps the dark matter that has a type of energy that gives them impulse, perhaps, or not.
Not particularly. I mean, it has its own gravity. So that's how we
Yeah.
spotted it. It has its own gravity. So it pulls stuff in.
Okay.
But unless it's coming straight in, it will always sort of swerve around at the last minute. As it gets closer, it gets sort of pulled into this vortex, and then it just stays in the orbit it ends up in. So
Thank you.
everything sort of settles out in the end, but it's only the beginning. Same happens in our solar system. The sun formed, and the planets all tend to be in the same plane, because that's kind of the plane it formed in. And that's where they scavenge the material to form from.
Just a little comment. Because we live on not the dark side, but we live in the unpopulated area, don't we?
Yeah.
Do you is it possible there's more likely to be life here? Is this like, you know, a bit like the center of an egg or something, where there's not much happening, even though we think there's a lot? And the rest of the universe, space, there seems to be so much going on. You know, all oops, I lost my earbud.
Yeah. No, that's a very good observation. I don't know, because we haven't visited
No.
places or
These
talked
are
to
all
anyone living
questions
there.
that pop
Yeah.
up. Sorry.
But
I'm almost not expecting you to know the answer to these, but
yeah,
it's just how my mind works.
I think
Lovely,
it's a
thanks,
very
Mel.
Thank you. Okay.
it's a very
Okay.
good observation, because if you are in a very chaotic environment, you know, we know that Earth life first appeared about 3.5 billion years ago, and it took a long while to get to where we are today. So if you have anything that happens during those 3.5 billion years that you're not expecting, you know, like the sun blows up or a galaxy passes through, then that's probably going to be bad for life with its you know, gradual improvement and evolution over time. So yeah, one of these more chaotic areas we think is probably bad. The same in our Milky Way. If you're right in the center, it's a very chaotic place where stars are all merging around. If you're out in one of these spiral arms, you get quite a lot of these big blue stars, which only last for a while before exploding violently. So that's probably a not good place to live. So somewhere nice, I like, you know, like a sort of cul-de-sac type road in the middle of the galaxy in a nice quiet part of the universe is kind of the most desirable place for life, I suspect.
We're in a good backwater, yeah. In the chat, MD says, please let me know why they're all such beautiful different colors.
Right, the colors really come from, and you know, they are slightly enhanced in that you probably wouldn't see them quite as bright as that if you were standing close by. It's the telescope. So the colors come from the different gases. So hydrogen gas, which is the most common thing, it makes up 75% of the universe, or the matter of the universe. That tends to glow in a sort of reddish color. That's its predominant color that comes from the emission spectrum. Oxygen and nitrogen and sulfur glow in slightly other colors. So it tends to be what's around at that point. And they're also slightly fake, well, not really fake, but the Hubble telescope, from which most of these galaxies are taken, is really a black and white telescope. It only picks up light, but it has a series of filters that it puts in front. So you get like a red filter and a blue filter and a green filter. but they tend to pick on certain elements. So they would go for a hydrogen filter that picks out the hydrogen, and a sulfur filter, and then an oxygen filter, and then they color them. Hydrogen they sort of color reddish, oxygen I think bluish, and sulfur yellowish. But you know, it's not like a picture you would take with a camera. You only get certain wavelengths because that's the particular ones that astronomers are interested in, that tells them the most about the detail. So there is a little bit of artistic license in some of these, but they try and make it as sort of true to real life as they can be, given the constraints. The James Webb's even worse because that mostly takes it in infrared. So you only see like shades of infrared. So it's not what you would see at all with your naked eye. But you know, they try and make them as nice as they can.
Lovely. Okay, we only got about another couple of minutes. So John, you make it a quickie, and we'll.
Yeah, I'll make a quickie. Thank you for a very interesting talk, Julian. I was thinking about the radio telescopes. What frequencies do they use? And if you use different frequencies, do they bring out different details in the gases and whatever you're looking at?
Yeah, I have to say I'm not really a radio astronomer, so I'm not. They tend to work in megahertz, I think. Wavelengths I'm probably better at, so centimeters to meters of wavelength, I think. Quite long then. Quite long, yeah. There's this big hole in the atmosphere where you can get radio waves through. If they're
So
even
that's why the Jodrell Bank telescope is so wide. So
yeah. So I think that's centimeters to meters, and there are certain things. There are certain key frequencies that. Again, I can only think in centimeters. So there's 21 centimeter line, which is where hydrogen has a particular transition. So if you're looking in that, you can see big clouds of hydrogen because the atoms occasionally flip from spinning like this to so symmetric spin to anti-symmetric spin, and they give off.
And do all galaxies produce radio frequencies like that you can observe?
Yeah. It has to be cold hydrogen to do that. So sort of 20 to 100 Kelvin, which is pretty chilly. So to do that, if you go much higher than that, you start to excite atoms to other things, and then you start to go into the visible light and even into the X-rays at that point. Yeah. So again, you need different instruments to get the different pictures. But yeah, so that tends to be why we do multimedia astronomy now, from just looking through a telescope. We can have a whole range from X-ray to radio to get a complete picture of what's going on.
Okay, thank you very much. Back to you, Neil.
Yeah. Okay, can I just squeeze one small question in, then and we'll wrap up if we're done. With the dark matter around galaxy, is the density very variable, or do you find large masses of dark matter in certain places and lower densities elsewhere?
You certainly find it around galaxies. I mean, we think the dark matter formed first, and then the other stuff fell into it. But there are places around where there's like clusters of dark matter with nothing obvious sitting in them. They're really difficult to map because they don't shine in anything. You can't detect them in radio, light, gravity. Well, you can detect them by gravity, but not gravity waves. So you really can only chart them by the influence they're having on other things around them. So there's a couple of techniques for doing that, usually with the bending of light. So light is bent by a big gravity field. So if you see light being bent in very extreme things, that's called strong gravitational lensing. You can see those. There's another one called weak gravitational lensing, where you get minor distortions to shapes, and you can sort of, by lots of maths and lots of computer number crunching, you can get sort of maps of where the dark matter is. Something I've not done. It sounds far too tricky for me to get involved in. Luckily, there are clever people who can do it.
Lovely. Thank you for that. Yeah. Well, thank you. I found it, and I'm sure everybody else did. Fascinating, beautiful imagery. Very interesting, very well put together. So, can we all unmute ourselves and give Julian a well-deserved clap and thanks.
Thank you. Thank you. Thank you very much. It was wonderful.
Thank you very much for inviting me.
Yes, I think
great.
we have strong recommendation here, Julian. Thank you very much. We really loved it. Thank you.
Okay, thank you very much.
Thank you.
Thank
Thank you.
Okay.
Thank you.
Take care, everybody. Yeah.
Take care.
Bye. Bye-bye.
Bye-bye.